Tonight, the sky changes the question. Astronomers look up and see a visitor that refuses the script. They call it 3I/Atlas, the third known interstellar object to slice past the sun, arriving with speed that compresses the clock. Instruments hum softly. The room quiets as numbers fight the models that trained them. Scientists are not afraid of monsters, they are afraid of blind spots. The fear here is rational. Measurements that misbehave, choices made inside a narrow window, and consequences that could spill into spacecraft, forecasts, and public trust. 3I/Atlas comes fast and keeps going. Its window is very brief. What if 3I/Atlas is not a comet in the way that matters most? 3 layers harden the question. First, the data carry shapes. Our models do not wear well, like brightness that grows unevenly across the face of its haze. Second, the time to aim telescopes and request observations is shorter than a news cycle. Third, the system around Earth is sensitive. Dust can charge, plasma can ring, and tiny errors can multiply through networks we depend on every day. That is why fear enters the room tonight, not as panic, but as purpose. Follow the signal, audit the instruments, treat every minute as evidence. Ask the only honest question: if it will not fit the story we brought to the sky, what story will it force us to tell next? Before 3I/Atlas took the stage, 2 messengers crossed solar floodlights and unsettled confidence. Oumuamua arrived first, thin on clues and heavy with consequences. Borisov followed, brighter and dustier. Together they taught a lesson that keeps control rooms awake. Fear, when earned, is a method. Oumuamua traveled on a hyperbolic path that signaled interstellar origin. Its brightness rose and fell in a rhythm implying an extreme shape, maybe sheet-like or shard-like, yet telescopes never resolved a reliable outline. Stranger still, its motion carried a non-gravitational push without the fuzzy shell and flowing tail that mark ordinary comets. Gas seemed absent, yet something nudged it. Explanations raced across whiteboards. Invisible hydrogen ice, a nitrogen crust from a far-off world, cohesive dust, thermal lag releasing jets too fine to see. Each idea solved one symptom while worsening another. Why did Oumuamua make our models hesitate? Because the engine behind the push stayed hidden. Because geometry, surface physics, and thermal history pulled in different directions. Because every simple repair created a new mismatch somewhere else. It became a question shaped like an object. Borisov, by contrast, looked like the comet teachers draw on chalkboards. A coma bloomed, a tail curved, and spectra reported familiar ices. The gas mix held unusually high carbon monoxide, a signature pointing to a birthplace colder than most entries in our catalogues. It was textbook in silhouette and unorthodox in chemistry, a reminder that interstellar space holds many climates. Set side by side, the pair hold a mirror to our blind spots. One breaks dynamics, the other breaks composition. One whispers without a coma, the other speaks fluent comet with a colder accent. Both deliver the same line. Our priors are provincial. What if 3I/Atlas inherits both mismatches at once? The alarm was quiet at first, a ripple in a status log that most eyes would miss. Then a thin streak crossed stacked frames, and the room learned a new kind of silence. Tonight, the clock began running faster than anyone had planned. A nightly sky survey in Chile pulled the thread. Technicians ran checks for hot pixels, satellite glints, and camera ghosts. The track held. A learning system linked detections across fields and reported a mover that did not match any catalogue. Cross-checks followed. Phone lines lit with calm voices. In the timeline of interstellar visitors, a third page started writing itself. Preliminary orbit fits pointed to an open curve, the signature of an object not bound to the sun. The inbound speed was high enough to fold the schedule. Brightness rose, but not cleanly. The cadence of the rise smelled like a comet, yet something about the shape of the haze refused easy labels. The word interstellar moved from speculation to baseline. The designation came next. From a temporary string to a formal name, the object became 3I/Atlas. Notices went out to the community with a crucial line. No impact risk to Earth was expected at this stage. Relief lived beside urgency. Requests for telescope time multiplied. Ground observatories raced the geometry of the sun. Space telescopes weighed angles, slews, and budgets. Weather, maintenance, and daylight conspired to cut minutes from an already thin window. Every approved exposure felt like a rescue of data that would not come again. If the first minutes slip, do we lose the fingerprints that tell us where this traveler was born and what it carries across the dark? Next comes the map. Why the geometry squeezes the window and how speed turns planning into triage for everyone watching. The map squeezes before anyone breathes. A hyperbolic path slashes through the solar neighborhood and the clock folds in on itself. With 3I/Atlas, geometry becomes a timer. Every rotation of Earth takes minutes off the ledger of certainty. A hyperbola is an open promise. Come in fast, leave faster. Excess velocity relative to the sun means the visitor cannot be captured, only sampled as it goes. The higher the speed, the steeper the schedule. Long integrations smear. Short exposures starve. Tracking systems strain to follow a point that refuses to pause. Solar elongation sets the first fence. Telescopes cannot work when the target sits too near the sun, so the best nights exist in narrow bands where glare drops and safety returns. Phase angle sets the second fence. At large phase, forward scattering can lift brightness, but morphology skews, hiding fine structure that timing teams need. Apparent motion becomes a mechanical test. At many arc seconds per second, stars become scratches unless mounts carry non-sidereal rates with clean precision. Slit spectrographs miss, imaging spectrographs compromise. One parameter improves while another slips, and the best trade moves every hour. Sight geometry adds more teeth to the clock. High air mass near the horizon fattens noise. Weather deletes nights. The moon pulls contrast out of the background. Twilight cuts the evening and the morning in half. Northern and southern stations hand off the target, but parallax and conditions never match perfectly. What if 3I/Atlas crosses the smallest elongation in a week of bright moon, and the only spectroscopic night dies under a stubborn cloud deck? Operations answer with triage. Queue schedules flex. Teams stack short sequences, bracket rates, and reserve contingency time. The plan is simple. Keep the window from collapsing before the data can speak. Dust hides the heart. In every frame, a soft cloud blooms and turns the nucleus into rumor. To learn what 3I/Atlas really is, investigators must read the fog, not the rock. The case begins with particles, light, and patience held on a tight clock. No telescope resolves the core cleanly. Size lives behind inference. Photometry sets a ceiling. Albedo assumptions set the spread. If the surface is dark, the body could be kilometers across. If it is bright, it could be a few hundred meters wide. Both pictures fit once the coma's glow is subtracted. The range is wide, but the logic is firm. An unseen core drives the show, and the show is dust. Morphology writes a moving diary. At some angles, the coma sharpens into a teardrop, the tail pulled by the solar wind. At others, fans open like folded paper, hinting at vents that switch as the body rotates. As phase angle grows, forward scattering brightens the edge, carving asymmetries that mimic structure and tempt the eye. Jets and rotation tie the pattern together. Active patches, warm as sunlight, sweeps across them. Fissures breathe. A slow roll turns geysers into metronomes, so a fan repeats in the same place night after night. The repetition is a gift. It lets observers time the spin and map active longitudes without ever seeing the core. Dust is a double-edged witness. It lets cameras see the visitor at all, then blinds the spectrographs that would weigh its chemistry. It scatters light, masks the nucleus, and drapes noise over detail. Every gain exacts a loss. What if the dust is not a side effect but a strategy, and we have misread the object from the first night? Under the veil, which gas rules the courtroom of this case? In the infrared, the scene turns into a fingerprint. Molecules write their names in light, and the spectrum becomes a transcript fit for a courtroom. Investigators aim instruments and wait for the lines to appear, precise as a signature. Method matters when the window is thin. Observers choose dispersers and slits, trade resolution for signal, and schedule short, repeated visits to catch the comet between glare and geometry. Calibrators run flats, darks, and standards. Every step disciplines the data so that the next paragraph can be trusted. The result strikes with clarity. Carbon dioxide speaks louder than water, lines rising above the baseline. Energy favors the gas that escapes first. If this balance holds, the coma is driven not by water ice racing to boil, but by carbon dioxide lifting off in steady flow. And that changes the thermal story. Other voices follow. Water is present. Carbon monoxide contributes. The continuum shows ice grains scattering sunlight. Trace features, faint, hint at more complex chemistry riding the flow. Together they paint a profile that is mixed, layered, and unfamiliar to playbooks shaped by local comets. Two paths explain the surprise. Perhaps the object formed or lingered in a realm where carbon dioxide freezes easily, far from a warm star. Or perhaps an insulating crust now seals most shallow water, forcing carbon dioxide from deeper pockets to dominate the outgassing. Both pictures carry different birthplaces and journeys. What if carbon dioxide is a mask rather than a face, and the nucleus hides a composition that only later sunlight can unseal? Caution stays in the frame. Dust reddens the continuum. Slit losses and pointing jitter can bias lines. Absolute calibration wobbles. The signal-to-noise ratio breathes with weather and time. Even so, the trend stays stubborn, daring modelers everywhere to answer with rigor. Fear has a history. Oumuamua cracked dynamics. Borisov cracked composition. 3i/Atlas arrives carrying toolboxes and a new manual. The lesson is not monsters. It is models that fail where confidence feels highest. That is why scientists flinch. Oumuamua wrote the first fracture. Its path was hyperbolic, proof of interstellar origin. Its motion carried a non-gravitational push, yet telescopes saw no coma. The engine behind the drift hid from view. Geometry, surface physics, and thermal stories pulled in different directions. Every simple fix created a new mismatch. Dynamics blinked. Borisov wrote the second fracture. It looked textbook in silhouette. A bright coma, a tail, and spectra that spoke fluent comet. Yet the gas blend leaned toward carbon monoxide, a cold signature uncommon in local catalogues. Composition blinked. 3i/Atlas stands in the doorway between those cracks. Its spectrum favors carbon dioxide over water. Its window is thin. Its morphology shifts with phase in ways that refuse easy templates. To pull an origin from these ingredients, modelers must juggle too many knobs at once. The map from cause to data is not one-to-one. That is the center of the fear. First, the inverse problem admits families of answers, not a clean identity. Second, priors trained on water-driven comets bias the search space and anchor teams to coastlines. Third, errors propagate. A wrong prior skews exposure plans, then skews the next measurements, then confirms the mistake. What if the prior is wrong at the root, and the community is calibrating the universe with a curved ruler? The fear here is therefore a discipline. Treat confidence as a suspect. Rebuild the ladder of assumptions. Demand independent checks. Keep alternative explanations alive until the data can evict them. 3. I/Atlas makes that discipline urgent. Invisible rain falls from a clear sky. Sensors hear it before eyes do. Micrograins touch metal at interplanetary speed, each strike carving a story smaller than a pinhead. Tonight's case file is dust, and dust is never alone. The threat is quiet and fast. Engineers define a hazard hiding between micrometer and millimeter scales. The coma and tail exhale particles into space. Flux rises and falls with geometry and time. When the radiant aligns with a spacecraft's motion, relative velocity amplifies damage like a headwind sharpening sleet. Direction matters as much as dose. Tiny shifts in angle change effective cross-section, turning safety into exposure. Non-spherical grains spin and skip. Fragments multiply the count. Navigation updates must happen in hours, not weeks. Operations must separate physics from grit in every frame. The consequences are mechanical and thermal. Whipple shields bruise and prove their worth. Solar arrays pit and lose efficiency. Radiators scar. Apertures fog. A single crater on an optical window scatters light into a ghost that haunts every later exposure. Most of this damage speaks softly and accumulates. Mitigation is procedure and posture. Spacecraft roll to present armor. Teams schedule sensor quiet times, delay filter changes, and limit slews. Ground planners hold small trajectory trims in reserve to dodge peaks that forecasts reveal. If the stream pivots without notice, are we shielding our back or exposing our flank? Next comes plasma. Charged particles and fields turn dust into interference. Electric space does not look like thunder, but it acts with the same nerve. Charged particles thread the vacuum. Magnetic fields herd them into invisible lanes. A dust-rich coma adds new charge carriers and new ways for power to move through the environment around Earth. Spacecraft live by balance. Sunlight knocks electrons free from surfaces. Plasma brings currents that push back. When the balance tilts, different panels charge to different voltages. The result can be a micro-arc, a spark you cannot see that still leaves a scar. Instruments reboot. Memory flips a bit. A quiet error becomes a wrong command. Radio pays too. Ionized tails bend and scatter waves. Deep space links hiss and fade. Navigation signals flicker as the path through plasma thickens and thins. To ground users, the symptom looks like dropouts and jumps. To controllers, it looks like a page of alarms. Here is the mid-hook. What if a coma enriched by carbon dioxide and fine dust shifts the local plasma enough to raise the rate of these events for days at a time? Mitigation is physics and patience. Constellations stagger operations, spread pointing angles, and slow, sensitive maneuvers. Space weather teams add the object to their forecasts. Operators bias power systems towards safety margins and watch for differential charging signatures. The plan is not fear, but posture. Electric space is a relay race. Every handoff between field and charge can carry risk today. Electric space does not look like thunder, yet it behaves with nerve. Charged particles thread the vacuum. Magnetic fields herd them into invisible lanes. When a dust-rich coma approaches Earth's neighborhood, the plasma grows thicker and power finds new paths to wander. Spacecraft survive by balance. Sunlight knocks electrons free. Ions arrive and settle. The system seeks equilibrium, but density changes tilt the scales. Different materials charge to different levels. A panel sits at one potential, a bracket sits at another. The gap can arc. A spark too small to see still writes a scar. Instruments reboot. A memory flips a bit. A quiet error becomes a wrong command chain. Radios pay the next bill. Ionized tails bend and scatter waves. Deep space downlinks hiss. Navigation signals jitter as the path through plasma thickens and thins. To operators, it looks like alarms. To users, it looks like dropouts and jumps. Midway through the watch, one question hardens. If a coma enriched by carbon dioxide and fine dust thickens the local plasma for several days, which constellations can hold margin? Mitigation mixes physics and patience. Fleets stagger sensitive operations, spread pointing angles and slow slews. Power systems bias towards safety. Teams watch for differential charging signatures and hand the forecast between ground and orbit like a relay baton. Electric space is not drama. It is drift. Vigilance is the method. 3I/Atlas makes the posture urgent for everyone. Order or fracture. That is the fork where investigators now stand. 3I/Atlas could be a gardener that seeds structure or a cue ball that scrambles it. The same coma that lights the way also hides intent. What matters is how the traveler couples with dust, gas, and time. In the Cedar picture, an interstellar visitor behaves like a condensation nucleus. It carries a recipe of ices and micrograins forged far from our sun. When sunlight wakes it, outgassing releases fine particles, raising collision rates and letting clumps persist. Jets repeat with steady rhythm as the body rotates. The coma stays smooth. The brightness curve tracks phase. The particle size distribution leans small. Grains, shadow grains, cooling patches, and stabilizing flow. The signature is constructive. The visitor increases sticking and leaves a region more prepared to build. In the perturber picture, the traveler is a stray marble shot across a crowded table. Its field, wake, and dust shed alter local traffic. Asymmetric fans persist. The apparent radiant of micrograins wanders, outgassing pulses and stalls. Clumps appear off-axis. Collision energies rise, fractures multiply. Instead of cooling patches, shadows sharpen gradients and drive shears. The signature is disruptive. Orbits wobble, streams split, and the nearby medium grows less predictable. How to tell them apart? Test the light. Track the phase curve night by night. Map the spin by timing repeating fans. Compare gas ratios as sunlight deepens to see whether carbon dioxide stays in charge or yields to water. Watch for torque. A steady, non-gravitational drift that flips when vents enter shadow reveals internal geography. Count particles by size over time and see whether the distribution narrows or frays, seeding or scrambling. Which side is right? If typical, models widen priors and retire shortcuts that assume water drives comets. The clock turns predatory when the target is interstellar. A mission to 3I/Atlas must outrun uncertainty before the window snaps shut. The speed is unforgiving, and every week lost becomes many kilometers per second that no rocket can buy back. The trap is time itself, and time is already moving. Engineers frame the problem in plain language. Excess velocity relative to the sun is high. Launch late and the required delta V climbs steeply. Launch early and designs fly half-finished. The window for a viable trajectory is narrow, shifted by geometry, and salted with constraints from weather and budgets. Cheap leaves first, expensive later, impossible by month's end. Architects sketch remedies that borrow speed. A fast flyby gathers what it can in minutes or hours, then falls behind. Gravity assists from inner planets can help, but only if alignments exist soon enough to matter. An Oberth-style burn near the sun multiplies energy yet demands heat shielding and timing that stretch hardware and nerves. Rendezvous is a dream that the calendar refuses to fund. Payloads learn humility. Cameras, spectrometers, and dust analyzers must work on arrival, without rehearsal or second chances. Autonomy grows teeth. Scripts branch around failures. Bandwidth is rationed. One shot stops being a metaphor and becomes a design rule. Midway through planning, a question freezes the room. If the launch window slips by one cycle, do we have ethical reason to hurl a craft that cannot reach its quarry? Risk fills the margins. Heat loads rise, attitude control fights at speed, dust storms the approach, and radio links bend in a coma. The rule is brutal but honest. Protect the vehicle unless the data will change the story. Next comes identity. 3 competing portraits of what 3I/Atlas may truly be. 3 portraits, 1 suspect. The same data can sketch 3 different faces, and the investigation must learn which lines are real and which are makeup. Tonight, the narrator lays them on the table and invites the evidence to argue. In the first portrait, 3I/Atlas is a comet born or parked in deep cold where carbon dioxide freezes. Sunlight wakes the skin. Carbon dioxide escapes first and drives the coma while scarce water lingers. If this picture holds, ratios stay high and steady as distance shifts, brightness follows phase smoothly, and dust sizes lean small. The object becomes messenger from a climate our local comets rarely recall, a chemical accent of exile. It is tidy, elegant, severe. In the second portrait, a crust insulates shallow water ice and throttles it. Dust, organics, and minerals sinter into a shell. Deeper pockets of carbon dioxide vent. So the coma looks carbon dioxide rich, even if the interior is mixed. Ratios evolve with sunlight. Torques rise and fall as vents pass into and out of shadow. Fans keep asymmetries that repeat with the spin. The mask is physics, not pretense. In the third portrait, considered with strict caution, something non-natural hides in the data. A sustained non-gravitational push that evades thermal answers. A chemical mix no ice or rock explains. Dust that breaks size laws. The burden of proof is towering. Simplicity cuts hard. The test is elimination, not wonder. But what if all 3 fit at once? Which lines are the face and which are disguises? The honest path is to try to reject each portrait before claiming one. That is the discipline, and the clock does not stop. Next, the report separates impact fear from the wider system risks that shadow this case. For the audience watching, this is not a collision disaster. The numbers say so, and the numbers are watched. They change, but they do not drift toward Earth. Reassurance here is conditional and earned one observation at a time. Panic is a story. Geometry is a fact. The path is open and leaves the sun. A hyperbolic arc misses Earth by a comfortable margin according to current fits. There is no intersection in space and time. The visitor passes, the planet remains a spectator, and the closest approach still lives far outside the envelope that would trigger kinetic alarms. Risk, however, is not singular. A strike is one class of danger, system stress is another. Dust can erode hardware, plasma can rattle radios, models can bend under priors that do not fit. The fear that matters lives in infrastructure, analysis and planning, not in cinematic impact. Uncertainty shrinks with each night. The cone narrows as tracking improves. Small forces can nudge the course, but the bounds continue to exclude an impact corridor by wide margins. Teams fold new astrometry into the solution, publish updates, and watch for outliers that hint at unmodeled pushes. Headlines will sometimes blur close pass into threat. Close in astronomy rarely means close in human terms. Precision survives by refusing metaphor. The orbit is calculated. The language should follow. If this is not a collision story, what warning lights deserve the watch? Keep the model honest and the telescopes working. The job is vigilance. Refine the orbit, separate hype from hazard, and prepare to measure the signals that truly matter. Take back the nights. After weeks swallowed by the sun's glare, the target will reappear in early December with workable solar spacing. Each night is irreplaceable. Miss one, and the timeline loses data no later exposure can replace. The plan reads like emergency triage. The window is thin. The first task is geometry. As elongation improves, phase angle still sculpts brightness and hides structure. Teams sequence exposures to catch low air mass, steady seeing, and the darkest hours. The rule is simple. Aim early, aim often, write everything down. Space assets lead the fingerprinting. The James Webb Space Telescope targets infrared lines to follow the ratio of carbon dioxide to water and to watch shifts as sunlight deepens. The Hubble Space Telescope adds ultraviolet imaging and narrowband filters that trace ions and fine dust. Together they search for slight non-gravitational accelerations hinting at evolving vents or hidden torques. Ground observatories fill the cadence. Optical and near-infrared cameras map coma morphology and the light curve. Spectrographs sample gas once per rotation to time jets. Radio receivers listen for plasma signatures in the tail. North and south handoffs keep coverage. Standards anchor the record. Core measurements are threefold. Track the carbon dioxide to water ratio over time. Image repeating fans to time the spin and map active longitudes. Refine the trajectory to measure tiny accelerations. Stop rules are explicit. If geometry degrades or the signal-to-noise ratio drops below thresholds, stand down and save minutes. If the first night loses spectra, does the entire energy budget slip one rung off, never to realign? Coordination completes the design. Global queues carry timely alerts, shared logs, machine-readable reductions, and archived calibration frames. Public preprints move fast. The handoff to Part 15 explains why earlier discovery power is the master key. Find it sooner or lose the story. That is the bargain Rubin Observatory offers anyone watching the sky for the next interstellar visitor. Early discovery buys nights, and nights buy truth. The instrument is built for this exact leverage: wide field, deep reach, and cadence that turns the sky into a movie. During the legacy survey of space and time, the telescope sweeps the heavens many times per night, reaching faint magnitudes across a field of view. Fast movers that would slip between programs leave paired traces in difference images. Software links them into short tracks, then a preliminary orbit flags the unusual. Objects that refuse a bound path. The processing chain matters as much as the mirror. Difference: imaging removes the static stars. Tracklets connect. The moving object processing system promotes candidates and posts alerts within hours, not days. That latency is the currency of rescue. It mobilizes follow-up telescopes before geometry steals the chance. What does earlier buy? More deep spectra under good phase, more rotations to time-repeating fans, tighter limits on non-gravitational accelerations, a longer runway to test whether carbon dioxide stays dominant or yields to water. Even the possibility of sketching a fast flyby goes from fantasy to feasibility when the calendar gains weeks. Here is the mid-hook. If the survey had caught 3I/Atlas 2 weeks earlier, how different would this report read today? Rubin is the early fence, built to keep surprise at the gate. Next comes a watch list, warning signals worth carefully tracking while the traveler passes. Rational fear is not panic, it is a method. It keeps hands steady on instruments and minds honest about the unknown. 3I/Atlas is not a verdict. It tests whether evidence leads the story, not the other way. So the conclusion is a responsibility. Publish errors before they turn into myths. Pair independent teams and require calibration files to travel with plots. Keep data open, timestamps precise, and assumptions written in ink. Let skepticism breathe, but do not let it stall the work. 5 warning signals deserve a standing watch. First, track the carbon dioxide to water ratio. A steady lead suggests deep origin. A slide hints at a crust that throttles shallow ice. Second, measure any stable non-gravitational acceleration. A persistent push ties physics to geography on the nucleus. Third, patrol the spectrum for unusual volatiles and changes as sunlight deepens. Mixed chemistry can betray hidden layers. Fourth, map persistent dust asymmetries that repeat with the rotation. Consistent fans mark active longitudes and reveal vents. Fifth, watch for plasma and electromagnetic anomalies, differential charging, radio fades, and navigation jitter lingering for days. The case ends with posture, not with drama. Act early, share quickly, and keep humility to change course when sky demands it. Coordinate schedules so silence in one hemisphere becomes coverage in the other. Protect instruments without protecting assumptions. Fear, when earned, is a compass that points toward truth. Keep the window open and let the next visitor find us ready, coordinated, and brave enough to measure what we would rather only imagine